That's kind of weird. Turns out it helps you turn the recording on for it to work out properly. All right, so today we're moving into what are called continuous distributions. So we've been dealing with like the binomial, the Poisson, negative binomial, etc., where you're going to get 1 or 2 or 3 or 4 blue M&Ms or whatever it is. Okay, how many baby girls did you have? Whatever it is, they are whole numbers. There's 0, 1, 2, 3, 4. That's it. Whatever their numbers are. Today we're going to move into continuous distributions. Okay, when I say you're 5, and you say you're 5'5", I'm going to call you a liar because technically, if I have a better tape measure, I can show that you're not 5'5". You're somewhere, whatever between there. How many height points are there between 5 feet and 6 feet? Infinite. Oh yeah. So we're all a little bit different. Okay. And so today we're going to talk about a couple of them. Tomorrow we get into the one I really want to talk about. But today, while you're just waiting for me, we're going to be talking about what's called a uniform distribution. Okay, and it's pretty straightforward, and it's pretty easy actually. It just says this is that your what we call PDF. Okay, PDF for this guy is literally. Where did it go? I was just going to write down what your book does. There it is. Yay. So f of x is equal to 1 over b minus a when x is between a and b. Okay? What do we mean by that? Well, we mean this. The height is, here's a, here's b. What we mean is the height is b minus a. And so this height here is b minus a. I'm sorry, the height is 1 over b minus a. The height is 1 over b minus a. And what do I mean by that? Well, if this is the height is 1 over b minus a. If this is 7 and this is 2, then the width here is 5. That means the height is 1 over 5 for an area of 100%. That's key. Everything we're doing has to have 100% or a 1 area underneath of it. Okay? And so when we start doing these, that's going to be the key measure here. It's pretty exciting. Of course, 0 anywhere else. What happens at, like 8, Groom? Well, 8 doesn't exist. That's like asking you what the probability of getting greater than a 7 on the dice is. That's not possible, sir. So we're not going to fool with that. Okay? And so it's really quite straightforward. You're like, Mr. Groom, what if I said to you, hey, listen, for instance, that one we just did, it's 1/7. Nice. From 1/5 rather. So f of x is 1/7. 0 elsewhere. And then again from, 2 to 9. Sure, why not? Nice. There it is. Yay. And so here's 2. Here's 9. Nice. And the idea is, and if I said to you, hey, what's the probability that x is between, or no, let's just say x is greater than 5. Well, I don't know, Groom. 5 is here. Boom. Well, that's a distance of 4. That's correct. 9 minus 5 is 4. You're right. So then that would be 4 times 1/7 is 4/7, or roughly, what is that, 56%. Give or take. Okay? 56%. What if I said, hey, what's the probability that x is less than 3? I don't know, but here's 3. That's 1 unit wide, so it's going to be 1 times 1/7, which is about 14%, give or take. Okay? It's that easy. What about between 3 and 5? Well, that's a good question, sir. What about the probability that x is between 3 and 5? It's an excellent question. I thank you for asking. It's 2 times 1/7, which is about, it's 2/7, which is about 28% or thereabouts, give or take. Okay? Piece of cake? Piece of cake. So one of the book examples is, the train is going to be here in a 15-minute time interval, and if it's a uniform distribution, so between now and the next 15 minutes, there is a what? Well, there's a 1/15 if you will, 1/15 probability it shows up, yes? What's the probability you have to wait more than 10 minutes? I don't know. Well, that's interesting because it's 10 times 1/15 is, well, no, not 10 minus. Come on, dumbass, pay attention. More than 10. I'm in this region, so it's 5. It's about a 33% chance I have to wait more than 10 minutes. Okay? So uniform distribution is really quite straightforward, honestly. It really is. We'll do a few more examples in the coming days of it, but there's not a whole lot to it, to be honest with you. Okay? It's really quite straightforward, honestly. Okay? Yeah. Piece of cake. Now, the one I really want to focus on myself a little bit of attention on today is this, what's called the exponential distribution. Exponential distribution. And you might recall that we talked about the Poisson distribution. This would be like customers per hour, per shift, per unit of time, if you will, right? And we talked about from that standpoint. And we said that, hey, mu is your expected amount of customers. Expected customers per time, right? And so we talked about that a little bit. Okay, now here's where it gets interesting. So this guy here talks about, this is customers per hour, if you will. This is time between customers. Well, what's that going to look like, Groom? That's a good question, right? So it's going to look something like, well, yeah, it's going to be, well, if it's going to be, let's say this is, so we get 7 customers per 1 hour, then the time is going to be 1 hour divided by divided by 7 customers. Are you with me? Right? It's the inverse of it. And so over here we used mu. Over here we're going to use lambda, where lambda is 1 over mu. Okay, it's just the reciprocal. And so what we're going to see is that the PDF for the exponential distribution is f of x is equal to, and typically in the real world we say f of t because it's a function of time, but whatever, lambda e to the minus lambda x. Okay, and then 0 elsewhere. Okay, I have to look because your book writes it in a way that I'm not. I always did it backwards from that. If that makes sense, right? So when I learned it, lambda was this guy, and then this was mu was 1 over lambda. It doesn't matter. It's just a different way of going about it. It doesn't make any difference to me how we get there. Okay, and so when we do these things, keep in mind this is always a continuous distribution. It's a big deal. This equation looks something like this, and it goes forever. Yes? Forever. And you're like, so what's your point, Groom? So that means the probability of any one point would be the number of outcomes at that one point divided by an infinite number of outcomes. But if I divide by infinity, isn't that basically 0? That's correct, sir. When we're doing continuous, this is true for any continuous distribution. The probability of any one number is 0. In other words, we won't be asking about what's probably it's exactly 5. We'll say it's less than 5, greater than 5, less than or equal to 2, whatever it happens to be. You with me? And so we're always going to be doing it in such a fashion that we end up with something that makes sense to us in this case, okay? It's always going to come out that way. So it's going to be, how do we get there? So the good news is if this were a class where you had to do calculus, you would start from here and you get to use a thing called the integral. And you're like, I don't want to. Good. We're not going to do that. And so what we're going to deal you is the CDF, and this is all we're going to ever use, is 1 minus e to the minus lambda x. That is the CDF. This is the probability that x is less than or equal to big X. Okay? So if I told you I had an exponential where lambda was equal to 0.27, just because I pulled that out of my butt, that's why. Hey, what's the probability that x is less than or equal to 3? I don't know. Let's plug it in. So it's 1 minus e to the minus 0.27 times 3. Boom. And if I bust out a calculator here, 1 minus e to the 0.27 times 3, about 55%. And you're like, oh, that's not hard. It's not hard. This is it. All you're going to be using is this exponential equation, this CDF. Now, the good news is Excel has a built-in CDF for it as well. Let me show you. So if you go into Excel and you go, oh, equals exponential dot dist, Hey, what does it want to know? Well, we want to know 3, because that was x. Lambda, 0.27, and always 1 on the cumulative, 55%, just like I did a minute ago. Are you with me? Just like I did a minute ago. But Groom, I know what you're thinking. What if I want x to be greater than? That's good. What's probably x is greater than 7? It's a good question, sir, and I thank you for asking it. Remember, this is what I want. This is what I can find, because this is the CDF. But I know that those two things add up to 100%. So this guy, greater than 7, plus this, or is equal to, rather, 1 minus that CDF business. Are you with me, sir? That's it. And so let's try that on for size. So not there. Let's go into here. Equals exponential distribution. Here it is. And I forgot to put the 1 in front of it. So 1 minus, add a bib. And then we're going to go, what did I say? 7, comma, 0.27, comma, 1. Always comma 1. 15% chance. That's it, babe. That is it. Easy money. Now, I know what you're thinking. I know what you're thinking, DA. I can read your mind. It's kind of obviously weird, honestly. Screw. Probably x is less than or equal to 6. Is that the same as probably x is less than 6? Less than 6? DA, you're right. Well, how did you know, Groom? Because what is the probability that x is equal to 6? Well, quite good question. This is a continuous distribution. That is, an exponential is. It absolutely is. So this thing here is equal to 0. So whether it's equal to or not equal to doesn't make a hoot of difference to me. Not a hoot of difference. It's like saying, hey, Mr. Grimm, there's a barbed wire fence on the edge of my property. Or a, let's say, I don't know, like not even a barbed wire fence, like a like this one single strand electric fence around the edge of your property. Oh no! It changed how much land I own. No, it didn't, stupid. It's literally on the edge of your property. It's not doing anything. If it was the Great Wall of China on the edge of your property, it's like 50 feet wide or something. Okay, arguably, yes. Okay, yes, that you did lose some property there, sir. It's a freaking one-wire electric fence. Your gooch. It didn't change how much property you had at all, sir. At all. Not even a little bit. All right, check this out. So let's say that at this restaurant, we should see 5 customers per, 10 minutes. Okay, cool. So that gives us what? It gives us 1 customer every 2 minutes, right? 1 customer every 2 minutes. Or if you prefer, customer, or it gives you 0.5 of a customer every minute. Now, you can do hours, minutes, seconds, whatever, but it's always based on time. What does that come out to be? Well, that's mu then. Are you with me? That's mu. Well, that means that lambda is equal to 2. Is that correct? Because it's 1 over 0.5, if that makes sense. Or it's 10 divided by 5, either way. So that's lambda. So when you do these problems, again, that's where you start out from. So, okay, so if I can see, if I'm getting 5 customers per minute, that means there's 2 minutes to deal with each customer. Does that make sense? That's the idea. Okay. Yeah. Right? So this is 2 minutes per customer. Okay. I don't know what you're doing, making them coffee, good for you, whatever. Hey, what is the probability that I will deal with more than 1.75 customers. Okay, I don't know. Let's find out. Again, in Excel, if I just use the formula, okay, more than is going to be greater than. So it's going to be equals 1 minus exponential dist. And then, what did I say? X was 1.75, comma, comma 2 is my lambda, comma 1. And there's about a 3% chance that I'll see that. Okay. And if you think about that, what does that even look like? So if you go into, if you go into Desmos, you can actually graph it. It's actually kind of cool to watch this. Okay. You can actually watch your probability do this thing. So if you do this, you go like, oh, okay, cool. So exponent, or you can go 2e to the negative 2x. That's my equation. Notice that my probability starts high and it drops off to 0 pretty rapidly, yes? But from here all the way to infinity is 1. But you would remark that this right here is most of the probability, yes? From here out is basically nothing. And in fact, that's what we just did. We did this. We did 1 minus e to the negative 2x. Negative 2, come on, dumbass. Let's go negative 2x. That babe. Notice how it started at 0. No probability here, yes, boom. And built its way up until right in through here. Look at where you're sitting. Dude, you're basically 100%. But if you look at it from here, that's 0.97-ish. Yes, 0.98-ish, whatever, if you will. That means that from here out is about a whopping 2% all the way out, the rest of the way out. And lo and behold, that's basically what we said, right? About 3%. Yeah. Oh, because we said 1.75. So if you were to come in here to 1.75, which is in this ballpark, yes, 1.75 is right there-ish. You can see you're right at 97%, right? And so from here out, the rest of it only adds up to about 3%. It's that easy, my friend. That easy. Now, what would happen, Groom, if this number was smaller? Good question. 0.05, 0.05. Well, it would help if we had a deal there. Well, let me zoom in a little bit. Hang on. Let me zoom in a little bit. You can see it does. Well, let me change it out. Just a minute, jerk face. You jerk. What a jerk, Groom. Come on. Being a dummy. Groom, you're such a ding-dong. Oh, yeah, that's what I'm talking about. Oh, dude, check this out. 0.0. No, 0, 0, 0, 0, 0. Give me 0. Add a babe. Up to 0.05. Oh, friends. Oh, that's actually, well, yeah, up to 0.05. 0.05. And so if you look at it, whoa, there it is. There's our guy, right? But look, it takes a long time for him to drop off. Yes? Does that make sense? It takes a long time for him to drop off. And it's going to take a while before we get down to 0. Yes? And so even though there's not a lot of area here, you have to go out a long way, so you're developing your 100%. But notice that if I put this back to 1, your probability does still grow pretty rapidly, yes? But notice that it takes you until you're over to around x equals, 1, 1.5, whatever, before you're over there. Oops, well, this one's wrong here. Hang on. Extremely forgot to change this part of the equation, you big dope. Now they match up. Do you see that? See how this blue line isn't going up nearly as fast as before, right? It's like when I get over to 20, I'm only up to about 60-something percent, 63% or so. Yes? That makes sense? Versus before, when I was over about 1.75, I was already at 97%. It's the same process, same idea there. Okay? And again, when we're looking at it here, we're talking about, hey, what's the probability that more than 10, remember this is minutes, or more than 1.75 minutes per customer. Okay? That's what that means. Okay? And so when I do this, you're like, okay, that sounds weird. But if you're doing this and you're like, if you say we average 2 minutes per customer, hey, what's the probability we have someone come and get all pissy with us because we spent it took them 5 minutes to get served or whatever? It's not going to happen. Are you with me? It's 0.00004. It's not going to happen. It's literally not going to happen. But it could happen. Okay, yes, it could, but it's not going to happen. Does that make sense? So when we start looking at this thing, you can kind of start looking at doing some statistics behind the scenes and going, hey, are we going to have people yelping about us because if we take too long, our customer service sucks? No, we're not. Not in this case. Not at all. Now, what if we lose some people? What if we lay somebody off and instead of having 12 little baristas, we only have 5 baristas? Well, what happens then? Well, and then all of a sudden now we're spending 5 to 7 minutes per customer. Well, then some people start getting pissy because they have to wait too long for their coffee. Okay, it went from being quaint to pissing me off, right? Oh, what a quaint little town! I love their little coffee shop. It's great. What do you mean I have to wait 10 minutes to get my coffee? You know,